In this video, I'll demonstrate how to tweak the guided simulation strength parameters to improve the quality of our destruction scenes and create a more natural effect. This video is a direct continuation from a previous video which covers all the basics for setting up the guided simulations. Please check out that video if you start to get lost. I'm going to add an extra video that will show you how to use all the skills covered in these two videos and reuse the same project HIP file to change the guided simulation and modify it even further. In the extra video, I'll be showing you how to go from a simple banana splitting geometry to a flower splitting geometry. You might be surprised to find out that you don't have to change too much to get from here to here. Just to be clear, the extra video is not a requirement. It's more like an example on some of the use cases of the guided simulation and how it can be used to make different types of scenes. As I mentioned in the previous video, I may make another video on using Mantra to do the shading and set up materials for this project, but that's still very much in the works and will come much later. Please keep watch for that video on my channel. Now let's come back to here. Let's go to the guided simulation. Setup here. Now this mode, it's set up to near point or near surface. Let's look at what we have here. Let's look at our guiding simulation. We have subdivisions like this. Our bend is applied like this. So let's template this. So this is what's going on. Now this RBD bullet solver is being influenced by nearby points. However, if you think about this, our guiding geometry, let's come here and let's look at the point. And let's only look at the point. So I'm going to switch this over to wireframe. I'm going to make the points a little larger. Do not have points inside at all. These points are only on the surface of our guiding geometry. So there's nothing influencing the fractured pieces in the middle, in the center. Our RBD solver, guiding simulations, is turned on to nearby point. The points from our guiding geometry for the interior piece is way too far. Our guiding geometry only has points on the surface. It doesn't have points in the inside. So this is a bit of a problem. It might not be too big of an issue if you're happy with this simulation, with what you get here right now. But if you want this guiding geometry to influence this RBD solver with higher precision, with more influence, then this will be an issue. Now, how do we get more points in the interior here without changing our bending animation? So we're happy, say we're happy with this animation. All we want is more points in the interior. Now let's come back over here to the point before we applied the subdivision. Instead of subdividing this, let's use the Boolean solver and slice this into pieces. Now I'm not going to go into too much detail into how the Boolean solver works with the slicing. I have a different video on that with a more detailed explanation. For here, this video is just mainly going to focus on guiding simulations. Here, now let's add a Boolean. Now I want to slice this cube into pieces, so I need a grid. Now the grid's way too big, so I'm gonna make it a little smaller, make it go up a bit, copy and transform. This is just a simple copy and transform. I need multiple copies of this, and I want to transform it a little higher. So what we have here, okay, maybe a little lower. Okay, that looks fine. It doesn't have to be exact. I'm gonna do this again, but I want this. So maybe I need a new copy and transform. Just over here, maybe too far. Okay. Copy and transform. Move it over here the other way. Okay, more of this. There we go. Okay, maybe one more. Now let's, I need a little bit more room, so I'm going to pull this down. These are my cutters. I'm going to merge it. So I'm going to be cutting this cube using these cutters. So it's going to be sliced into pieces. So let's hook this up to the boolean. In the boolean, I'm going to treat, now these are surfaces, and I'm going to do a shatter. Next, I'm going to add an exploded view. So I can actually see what is happening. This will be black because this is only for demonstration purposes. Now we have more pieces. This way we don't change our geometry. This doesn't change this original geometry, the shape of it. It doesn't change it at all. It keeps it while giving us that topology. Because these are individual that are not welded together. So if I take one of these pieces and I'm going to move it out. So these are individual blocks just being stacked on top of each other. Now we need a slice in the middle here too. So let's add another grid. Oh, not this one. Let's copy that over here. Template original, rotating on this side. Let's move it over a bit this way. Okay. Next, copy and transform. Okay, and add more. I think that okay, that looks good. And then merge it with, so these are my cutters. Let it slicers. Oops. Render the boolean, exploded view, so we know what's going on. So now we have pieces. We have individual blocks. So let me expand this, make it smaller, so you can see where the pieces are coming from. This is our original geometry. This is our sliced up geometry. What we have done with these cutters or these slicers is that we have sliced it on the side, the front, and the top. We're going to be using this geometry as our guiding geometry, and we're going to apply the bend on this. I'm going to take a look at the points, and I'm going to put this in wireframe. We have points inside in the interior as well, so we have more influence points. So let's hook this up to, oh, we don't need the subdivide anymore, so I'm going to ignore this. Move this over here. I'm going to keep it here for reference because I'm going to be sharing this file. So let's hook this boolean over to the bend, and let's look at what. Well, let's take a look at what it looks like. Now let's just scrub through the timeline. Looks good. It's still bending the same way. So let's hook it up back to the subdivision, and let's just do a small comparison. So the way that it bends, it bends exactly the same thing, almost exactly the same thing. There might be like a slightly of a difference, simply because the way I've sliced it has different topology than compared to how it's subdivided. The subdivision is more even. The way that I have sliced it in this over here, it's not even. Some pieces are a little larger, some are a little smaller. You could take more care into slicing it, but for this demonstration purposes, this will be fine. Then we move it over a bit. So this is so we give it a bit of room before we mirror it in order to help the simulation, to tell the simulation this is going left and this is going right. Now let's go back to the RBD solver and let's just play it. Now the next thing I want to talk about is this strength, this distance to strength. So what this is saying, this is the strength of how much this guiding simulation is influencing this RBD bullet solver. This is set to 1 right now. So let's see what happens when I set this to like 4 and just play it. I don't know if you can tell. Some of these pieces here, they're shaking a bit because being forced out of place because there's no room. As we bend it, there's less room on the bottom and some of the pieces are getting popped out. Since I turned up the strength of the influence of the guiding simulation, it's being pulled back. It's saying you're not allowed to pop out yet. You see, you still have to follow the guide. Let's also turn on the visualization for the guide. So RBD bullet solver, visualize tab, show guided. So if we check this, you can see that some of these pieces are being highlighted in blue. The ones in blue mean that it's still being influenced by this guiding simulation. The ones that are not, like the pieces over here, they're not highlighted in blue because they popped out. They're long gone. Now look what happens when I go back to the guided simulation, and I'm going to turn this back down to 1 and I'm going to run it again. So right here, we still have a lot of pieces that are being influenced, but once we hit past, so this is frame 14, frame 15, 16. Now we're losing it. We're losing everything. Okay. Almost all the pieces. The majority of the pieces are all gone. So let's turn this back up to 4. Now, we've long passed. This is frame 14. All the pieces are still being controlled by the guiding simulation, as opposed to what it did before. When the strength was set to 1 on frame 14, we lost like a good majority of the pieces already. So this is still being controlled. You might ask, like, why don't we just like pump up the strength of the guiding simulation so we get exactly what we want? Well, if you look at this, focus on this piece right here. I'm just gonna scrub back and forth. It's shaking. It's popping in and out. It's trying to get out of control, but the strength, the influence is too high, so it's shaking. I think to better illustrate this, I need to make a flip book. These pieces are just shaking all over the place. Like it doesn't look very natural. I'm gonna make another flip book. Okay, I just want you to see, compare this one and this one. So the one on the left has the strength set to 1. It doesn't shake. I mean, it doesn't shake as much as this one. This is like on the fritz. This one here looks more natural. So that's what happens when you have the strength of the guiding simulation set too high. It's the forces, the pieces in the middle, they don't know what to do. They want to break out of control because there's less room. They're being forced out of their confined spaces. But at the same time, the strength is set too high and it's being pulled back. And that brings us to distance to strength. Now, as the fractured geometry is being influenced by the bending geometry, some of the pieces on the bottom get popped out, as well as some of the pieces on the top, but more so on the bottom. As the fractured geometry bends, there's less space on the bottom. So let's take a look at this bend. Now, as you can see here, there's less space. Now, this geometry is actually deforming, but our fractured pieces cannot deform. So as this bend is happening, our pieces on the bottom here, they're gonna get popped out because there's like no space left. They're being pushed out of their confined spaces. So as they get popped out, they get further away from the guiding simulation, and this creates a bit of distance. Now, that's the distance that this parameter is talking about, distance to strength. The larger this distance gets, the guiding geometry will have less strength and less influence on these pieces. So as you can see, these pieces that get popped out completely, and it's so far away from the guiding simulation that it just completely lost it. The strength gets weaker and weaker as the pieces move further and further away. Now, this drop-off point where it loses all the highlighting and loses all influence by the guiding geometry, it needs a graceful fall-off. That's where we have this range we can specify in the parameters. This remaps the distance to the strength. At a distance of 0, when the pieces are closest to the influence points in the guiding geometry, it's at full strength because we have set the strength multiplier to be 1. So this is a multiplier. It gets multiplied to the actual strength value. Anything times 1 has no change. When the distance reaches 5, the distance will be reduced to a quarter of the original because our strength multiplier is set to 0.25. So if I have my strength value set to 4 times 0.25 equals 1, that's a reduced value. Now remember, this is a range, so there are values in between as well. It's implied in the remapping. For example, the strength of a piece that is at distance 2.5, which is the midpoint distance range, will remap the strength to 0.375 strength multiplier. Now, why would we need this distance to strength? Now, that's because after the pieces pops out, you don't want it to continue to follow the guiding simulation. Otherwise, you're going to have that shaking effect. After the pieces get popped out, you want gravity to take over. Or if you have any external forces, to naturally take over that piece. So this will create a little bit more realistic simulation, like a more natural effect, as when I compared the simulation when we had strength set to 1 and the one that we had strength set to 4. And also, this distance to strength makes it a gradual fall. Our guiding simulation sort of slowly transfers it to the gravity. Sort of like, oh, this piece, I'm going to slowly hand it to you, rather than just like drop it to the gravity and the gravity just suddenly takes over. It's going to be very apparent. The guided simulation gets really interesting when you start to think about questions like, what happens if the pieces collide with something in the path of the bending animation? So what if something's in between the guided simulation? Like, what if I had a collision object in the middle? Like, what would happen then? In order to illustrate this, I'm going to throw down a shader ball right in the middle of the path of the bending geometry. And then we'll take a look at the pieces that collide with it and see what happens to them. So over here in the RBD bullet solver, fourth input, we have a place to stick the collision geometry. So here I'm going to throw down, first I'm going to throw down a shader ball. So let's just template this. I want to put it on the side so I can see what happens to the pieces when they collide with this shader ball. Now we're gonna connect this shader ball to the collision geometry in the RBD solver. So that's the fourth input. Put the render flag on the RBD bullet solver, and we're just gonna play it. As the pieces start to collide with the shader ball, it instantly loses the blue highlighting. So you can see that these pieces, it becomes really more apparent on frame 13, lose the highlighting completely. As opposed to this side, we can see that there's nothing colliding with it. It's still being influenced by the guiding simulation. So as we advance through the timeline, it all falls apart. So we can do this, make this a little more apparent, is turn up the strength. I'm gonna let's make it 4, since we did 4 before, so we know what it looks like. And this is just a test to see what happens, what is actually happening when our fractured pieces that are influenced by the guided simulation, what happens when they collide with the shader ball. So I'm just gonna rewind it here. Now, these pieces here are being pushed by the shader ball. Eventually, push comes to shove, and this whole chunk of fractured pieces lose control. What we can conclude from this is that when the pieces start colliding with the shader ball, they immediately lose the influence by the guided simulation, meaning that the collision forces take over, or they have higher priority over the guided simulation. When the pieces collide with another object, which is our shader ball, the solver needs to make a choice. Should we continue to follow the guided simulation, or should we collide with the object? So either it goes through the shader ball, or it collides with the shader ball. It bounces off the shader ball. So going through the shader ball wouldn't actually make sense, because that's physically impossible. That's when it makes a choice. Over here, we can still see that certain pieces are still trying to follow the guided simulation. So we can still see that there's blue highlighting here. But once it gets far enough, it gets pushed over. Eventually, the collision geometry wins because it has higher priority. Remember to check out the extra video, which reuses the same project file and continues right where we left off. I'll make small changes to the guiding geometry and create a flower splitting visual effect scene. As I mentioned at the beginning, I'll be posting a Mantra video, and I plan to use this project to demonstrate how to start shading in Mantra and set up materials. It's still in the works, and even though Houdini 18 came out with Karma, which will eventually be the full replacement for Mantra, I feel like Mantra is still a topic I need to cover. Karma is still in beta. There are a lot of features that are missing in Karma and will have to be patient. But I still value the skills we can learn in Mantra, because I think the basic concepts in shading will still be used in Karma. It's not like Side Effects is going to reinvent the wheel. There will be pieces of Mantra that will be reused. Maybe certain design concepts or some of the UI design in Mantra can still be applied to Karma. Who knows? So there's still value in learning from Mantra. The only thing I have against Mantra is that it's very, very slow. And you need a monster PC to make anything that's production ready. Compared to Redshift, it's like heaven and earth. So I usually favor Redshift, and all my example animation clips are rendered using Redshift. But Redshift is a biased rendering engine, so it's technically not fully realistic. And Mantra comes out of the box with Houdini, so it's definitely worth going over. Thank you for watching and sticking to the end.